Hello class, welcome to this lesson on 5.3 on binomial distributions. So today we're going to be talking about computing probabilities for a value of a random variable from a given binomial distribution. So we want to be able to find the exact probability for x successes and n trials of a binomial experiment, as well as find the mean, variance, and standard deviation for the binomial distribution. We're also going to introduce the concept of a probability distribution and just kind of review those concepts as well. So the vocab includes the binomial experiment, the idea of a random variable, probability distribution, discrete random variable, and continuous. So let's talk about probability distributions and introduce the idea of random variables. So remember that a variable can assume different values. So x equals 1 or 2, for example. Now in this unit we use what are known as random variables. So a random variable is a variable whose values are determined by chance. So for example, if a die is rolled, x can be used to represent the outcomes. In this case, x would be equal to 1, 2, 3, 4, 5, or 6, which are the outputs of a single die. Now take another example. If 3 coins are tossed, then x, or any other letter that you want to choose, could represent the number of heads, such as 0, 1, 2, or 3 heads. Now for this example, we're going to actually group the possible outcomes by the number of heads obtained for the 3 coin tosses. So if we do that, well, we can have 3 tails, we can have 2 tails and 1 heads, and those are the different possibilities of doing that. And then we can have 1 tail or 2 heads, we can have all 3 heads. So this forms what we call our sample space. And we basically broke it up into the random variable, which is the number of heads in this case. So notice that the number of heads, 0, 1, 2, or 3, is based off of chance. And the chance is based off of how many belong in that sample space. So we can summarize the probability distribution in a table format as follows. So this is the value x, which in this case is the number of heads. So we can have 0, 1, 2, or 3 heads that is possible for this binomial experiment. And then the probability of getting 0 heads is 1 out of 8 possibilities. For 1 heads, it's 3 out of 8 possibilities. So that's the probability is 3 out of 8. And then again, another 3 out of 8, and then 1 out of 8. So this is what we call a probability distribution. Now notice that this probability distribution, that the probabilities add up to 1. So if we were to add up these probabilities, you're going to get it equal to 1. And notice that none of these probabilities are negative or 0. This is actually a requirement of a probability distribution, is that the probabilities have to add up to 1, and the probabilities themselves cannot be negative or greater than 1. So we can represent this table or probability distribution with a histogram or some type of graph. And this is how the distribution looks like. So notice it looks symmetric. It almost looks like a normal distribution in this example because of how symmetric it is. So it's very reminiscent of that. So this is how you would actually draw it. You would do the probabilities on the y-axis, and then the random variable, this is the random variable x, on the x-axis. Alright, so the definition of a random variable or a distribution. A random variable, again, just to kind of re-emphasize, takes numerical values to describe the outcomes of a chance process. So it's due to chance. The probability distribution of a random variable gives its possible values and their probabilities. So like the chart that we had earlier. Now there are 2 types of random variables, discrete and continuous random variables. So a discrete random variable takes a fixed set of possible values with gaps between them. So for example, gaps between them, meaning this means that usually we're talking about whole numbers, right? So with gaps between them, so like 1, there's a gap between 1 and 2, between 2 and 3. And let's say we can only use 1, 2, and 3. We can't use 1.5. We can't use 1.2. So no decimal numbers, basically. the probability distribution of a discrete random variable x lists the values xi and the probabilities pi. And you guys saw this example earlier with the heads example. In this case, it was 0, 1, 2, and 3. And then you can repeat if you're doing more coin tosses, for example. And then the probabilities were given on the bottom. So just an example of that. Now, we mentioned earlier that a probability distribution must satisfy two requirements. The probabilities have to be between 0 and 1, and then they have to add up to 1. So basically, the sum of the probabilities of x has to equal 1. So that's the second condition. And then the first condition states that the probability p of x for a random variable x has to be between or equal to 0 and 1. We kind of mentioned this earlier in an earlier probability unit, I believe unit 4, but we're emphasizing it here for distributions. So example of a discrete random distribution is like the coin example or the die example, where they're whole numbers 1 through 6, or 0 heads, 1 heads. You can't get 1.5 heads, for instance. So that would be discrete. Now, something that is continuous can take on any value in an interval. So in that case, for example, if we're talking about the volume measurements in milliliters, something that you can measure of Coke cans taken from a manufacturing line. The measurements here would differ due to chance and can be considered a random variable. So you're taking Cokes from a manufacturing line, so a factory line, and each Coke will vary by a little bit from the next. And that's because of random fluctuations in how much the machine fills the Coke cans, right? So there might be a difference of 1 milliliter, 2 milliliters, maybe as much as 10 or so milliliters between each Coke can, and therefore it's based off of chance. All right, so now we're going to introduce the idea of a binomial experiment. So now that we know what a random variable is, we know what a probability distribution is. Let's discuss a binomial experiment and distribution. So one type of discrete probability distribution is the binomial distribution. Again, this is discrete because it's going to involve, yes or no type of thing, or like a number 1 or 2 or something like that. Okay, so we're talking about discrete stuff here. So bi is going to be equal to 2. So that's why it's called binomial. And then nomial means name or category. So basically, binomial means that you have only 2 things that can happen, 2 outcomes, or 2 categories, if you will. Or it can be reduced to 2 outcomes. So for example, heads or tails, male or female, win or loss, true or false, etc. Anything that can be reduced to 2 outcomes is considered binomial. So situations like these are binomial experiments. So a binomial experiment is a probability experiment that satisfies these requirements. There must be a fixed number of trials. So like if you're tossing a coin, let's say you're tossing it 6 times, the number of trials in that case would be 6. It has to be a fixed number of trials. Now each trial can have only 2 outcomes, or outcomes that we can reduce to 2 outcomes. So that is the main purpose of why it's called binomial. So it has to be 2 outcomes. Now they're normally considered success or failure, the outcomes. The third requirement, the outcomes have to be independent. So remember that if you're selecting cards without replacement, for instance, that would be considered dependent. So an example of this is if you select cards with replacement. So selecting cards with replacement or selecting items with replacement is considered independent, right? The probabilities are considered independent. If it's without replacement, it's going to be dependent and therefore will not be able to satisfy a binomial experiment. So the fourth requirement is that the probability of success must remain the same for each trial. This actually ties in with the select the cards with replacement as well. So if you don't replace the cards, let's say you're selecting a card from a deck and you have 52 cards, if you select one and you don't replace it, well then now you have you have 51 cards left in the deck, so that changes the chance of drawing a different card. So in that case, the probability of success did not remain the same. So therefore it changed, and therefore it's not considered a binomial experiment. Keep in mind that the word success or failure here does not mean that something good or positive has occurred. For example, the number of successes could represent the number of people who were in an accident, in which case that's not a good thing. However, when we're talking about an experiment, or if we're interested in the number of people that were in an accident, in our binomial experiment, that would be considered a success. The failure in that instance would be where that did not happen, in which case where people were not in an accident. So let's look at an example. We want to decide whether each experiment is considered a binomial experiment. If not, state the reason why. So part A, selecting 20 university students and recording their class rank. Selecting 20 students from a university and recording their gender. Drawing 5 cards from a deck without replacement and recording whether they are red or black cards. Selecting 5 students from a large school and asking them if they are on the dean's list. Recording the number of children in 50 randomly selected families. So hopefully you kind of thought about that. We're going to go ahead and go over the responses for those. So for part A, no for part A, because there are 5 outcomes. If you're talking about class rank, well, you could be freshman, sophomore, junior, etc. So there are actually 5 outcomes, which is more than the 2 outcomes that are required for it to be binomial. Now for part B, yes, it can be considered a binomial experiment since there are 2 outcomes and the events are independent from each other. For part C, no, because the cards are not replaced. Remember that if you are selecting cards without replacement, then the events are considered dependent or not independent because the probability changes throughout the experiment. Part D, yes, there are 2 outcomes whether you're on the dean's list or not. And then the last one is not a binomial experiment because there can be more than 2 answers for any given response for the number of children. So you can have a family that says they have no children, in which case that would be a random variable 0, or 1 child, or 2 children, 3, and so on. Alright, so now let's talk about a binomial distribution. So we mentioned what a binomial experiment is and the 4 requirements for an experiment to be considered a binomial experiment. So now the results of the binomial experiment give rise to a distribution that is called the binomial distribution. So again, that's the definition. The outcomes of a binomial experiment and their probabilities are called the binomial distribution. Now I went ahead and provided a couple of graphs so that you can kind of see how the binomial distribution actually looks like. So notice, this is the binomial distribution for different number of trials and then different probability of success. So remember that, so note that the P here is the probability of success, and this is the number of trials. Remember that one of the requirements is that the number of trials must remain fixed for a binomial experiment. So in this case, this is n equals 15, a fixed number of trials. So let's say the probability here is 0.2 or 1/5. So let's say you have like 5 disks numbered 1 through 5, for instance, or something like that. And the probability of selecting a particular disk is 1 out of 5. In that case, and let's say you're doing this experiment 15 times. So that would be 15 trials, and the probability of success for selecting a given card is 1 out of 5. Then the results will look like this. So notice we drew a histogram, and the number of successes in this case could be, for example, how many, like let's say you have disks numbered 1 through 5. What's the let's say X is the number of ones that you choose. For instance, this would be considered binomial now because you could either choose the number 1 or you cannot choose the number 1. So that would be considered binomial. So either 1 or not 1. Those are my 2 outcomes. So therefore, the probability of getting a 1 will change, or will stay the same. It's 1 out of 5. However, the number of ones that I can draw from the disks can change based off how many trials I do. So let's say on the first trial I draw a disk of the number 1, and then the second trial I do not. Well, then at that point I did 2 trials and I only got 1 disk, right? So I keep repeating this 15 times, and if I do this 15 times and I get, for example, 8 disks, with the number 1, then that would be over here, 8 disks. And then I would record, my probability of doing that for that experiment. So this is what is meant by doing this. Now notice that the probability is very small for getting 0 of that disk, right? For 0 of the number 1. And the probability is also very, very low as you get to the number 15, because the probability of getting 15 disks, 15 of the same disk in a row, is very, very small. So therefore, this makes sense that the probability is going really, really low, almost 0, but not quite. And then the probability of getting a disk that is the number 1, for instance, about 3 times is very high. So it's about a quarter chance to get that. So this is how you kind of read the binomial distribution graph. Again, this is the same thing here, but you have 15 trials and a higher probability of occurrence. So if you have a higher probability of success, this means that there's a good chance of that happening, which means that your average value should be higher here, right? You got 12. It can happen 12 times with a probability of 0.25, which makes sense based off of a very high probability here. All right, so being able to interpret these diagrams is going to be useful. But notice also that as the probability goes to both extremes, 0.2 and 0.8, the graph is actually more skewed. So this is kind of skewed to the left here. This is skewed left. And then this graph where p is 0.2, it's actually skewed to the right. So it's not quite a normal distribution. But when you go to a probability of about 0.5 with a relatively high number of trials, in this case we still got 15 trials, but the probability is like average, like a coin toss, then it starts leveling out and you start having more of this normal distribution. So it starts approaching a normal distribution if the probability is about 0.5. So it approaches a normal distribution. So this is an important characteristic and will actually be used in a future chapter as well, or a future lesson. All right, so now let's actually look at how do we calculate the binomial? Like how do we get those values from that binomial graph that we saw earlier, those 3 graphs? How do we actually calculate those? So let's look at this example. Let's say you toss a coin 3 times. What is the probability of getting exactly 2 heads? So let's do the sample space for tossing a coin 3 times. Well, you can have all 3 heads. You can have 1 tails. And there's 3 ways of getting all tail or 1 tails. Then we can have 2 tails. In that case, there should be 3 ways of doing that. And then lastly, you get all tails. So in that case, we have a total of 8 possibilities, right? And the probability of getting exactly 2 heads, so we're going to say x is the number of heads, so x is equal to 2 here. So the probability of x equaling 2 is equal to, well, there's these 2 heads here, so 1, 2, and 3. So there's 3 out of 8. So that's one way of actually calculating it using the sample space. However, we're going to be using another method, the counting method. So basically the last unit that we did, where we did counting and permutations, combinations, that kind of stuff, we're going to be doing that here. So how do we go about doing that? All right, so if we want the probability of getting 2 heads, well, let's do what's the probability of getting heads or tails? So in this case, let's consider whether this is a binomial experiment. So in this case, this is definitely a binomial experiment, right? Because you get heads or tails. And the probability of success, the probability of getting heads, this is success here, which in this case is heads, is going to be 1/2. The probability of getting 1/2 from a coin toss is, or probability of getting heads from a coin toss is 1/2. So we're going to do that here. So we have 1/2, but we have 2 heads, right? So it's really 1/2 times 1/2, right? Heads and heads. So remember, when it's and, you multiply them. So we want heads and tails, right? What's the probability of getting tails? Well, that's going to be called Q. Q is the probability of failure, which means the probability of not getting heads, which means tails, which in this case is still going to be a half. So notice that those two always add up to a probability of 1. So the probability of getting tails, so these are my two heads here. Now we're going to do the probability of tails. So that's it. So that's my probability for those three. Now, remember that here that I can choose HHT, or I can have THT, or can I have THH, or I can have HTH, right? So there's three different ways of getting two heads here. So therefore, we have to have a number here, right? We have to have a number, a multiplier. We have to have a 3, right? 3 times that, because we have this 3 times. This is occurring 3 times. So how do we go about generalizing that, though? Well, notice that this is just a number of groups that we can choose, right? So number of ways that we can choose stuff. So we can write this out as the number of ways. So we can write this out as the combination. Remember that this can be considered as a combination when you're selecting stuff. So you have 3 coins, and you're choosing 2 of them to be heads. So the number of ways in which you can get 2 heads is going to be 3 choose 2. So that's how you find the total number of heads here. And notice that 3 choose 2 is going to be equal to 3 here. All right, so that's how you get this. So now that we got the idea of the combination, right, the whole combination idea, so it's 3 coin tosses and you want 2 heads. Now we're going to rewrite this as 1/2 to the 2nd power. And that's because that's for the heads. And then we're going to write the tails as just 1/2. So this is for heads, this is for tails. 2 heads, 1 tails. And so this is going to be my probability that x equals 2. So now this is my formula right here. It's going to be 3 times 1/2 squared times 1/2, or 3 times 1/2 cubed. And if you did that, you're going to get 3/8, because 1 cubed is 1 and 2 cubed is 8. So and then 3 times 1/8 is 3/8. I'll go ahead and show my work here. This is going to be 1/2 cubed, and then it'll be 3 times 1/8, which is 3/8. Okay, same answer that we got before. Now, why did I go through those motions to get that instead of doing the sample space? Well, because what if you had 50 coin tosses and you wanted to figure out the probability of getting 5 of them? Well, in that case, it's not very advantageous to do the sample space in that case, right? Because there's going to be a lot of possibilities, and that's why we introduced the counting methods. So you can always use this formula right here. This is called the binomial formula. So we're going to rewrite this out as P of x equals, let's say we want x successes, right? So, and we have n trials. So this is the number of trials. Let's say we have n trials, and x of them are the number of heads, for instance, or the number of successes. Remember that this is the probability of success. So I'm just going to call that P, and that's raised to the 2 power. That matches with this, right? That's because we wanted 2 heads. So in this case, if this is x, well then this has to be x. So P to the x power. And then what is this guy? That is just going to be Q. We call that Q, which is the probability of failure, which in this case, remember, this success is heads and failure is tails. And then that's raised to the 1 power. How do we get 1 power? Well, we had a total of 3 trials. 3 take away 2 is 1. So it's going to be n minus x. All right, and there's my formula. We're going to go ahead and reiterate that formula in the next slide. So that is the binomial probability formula. So in a binomial experiment, the probability of getting x successes and n trials is given by this formula. Now this may look different than the formula I wrote, but remember that this right here is considered to be the combination formula from Unit 4. So this is actually can be written as the combination of n choose x, or you could just say n choose x, times p to the x, q to the n minus x. So it's really the same formula. You can also write this out, or you can also write this out as n choose x, p to the x, q to the n minus x. Okay, and remember to find q, all you have to do is take 1, so the formula for q is equal to 1 minus p. So if you know that p is 1/2, then q is 1/2. If p is 1/3, q is 2/3, and so on. So that's how you find q. So again, listed below are the symbols. So again, p is the probability for success, q is the probability for failure. And to find the probability of failure, you just take 1 minus p, which is what I said earlier. Remember that n is the number of trials and x is the number of successes. All right, so now that we know the formula for the binomial probability, to find binomial probabilities, let's go ahead and apply that. So a survey found that 1 out of 5 Americans says he or she has visited a doctor in any given month. If 10 people are selected at random, find the probability that exactly 3 will have visited a doctor last month. So if we have 10 people, that means we can think of it as 10 trials. So we can think of our n as being equal to 10 here. Now it says that 1 out of 5 Americans says he or she has visited a doctor in any given month. So we're going to say that has visited a doctor is considered success. Now it says that exactly 3 have visited a doctor last month. So basically what they're asking for is the success. Okay, so whatever they're asking for is considered the number of successes. So in this case, the number of successes is considered to be x, and that's equal to 3. Again, remember that x is the number of successes in the trials, and then this is the number of trials. So, and this is considered a binomial experiment because you either visit the doctor or you don't, okay? So binomial experiment, visit or not visit, okay? So there's only 2 outcomes here. The probabilities are independent. Each person is independent from the other. They have no influence on each other whatsoever. They're selected at random. The number of trials is fixed because you're choosing only 10 people. So therefore, this is considered a binomial experiment. All right, so now that we know it's binomial and all that, we can go ahead and calculate the probability that x is equal to 3. So remember that the formula was the combination, right? So I'm just going to go ahead and write it out with the formula here. It's n choose x, so 10 choose 3. If you like to use the combination, you can write it like that, just like that. I'm going to write it using the parentheses symbol, but you can also write it like this, okay? That, and then times p. What is p in this case? What's the probability of success? Well, it says 1 out of 5 Americans achieved success, meaning visited a doctor. So this is going to be the probability, which is little p, is equal to 1 over 5, 1 out of 5 Americans. So if p is equal to 1/5, this means q is equal to 1 minus 1/5, or 4/5. Okay? Remember, these always have to add to 1. So that's q and that's p. So we can plug them in. We have 1/5 raised to the 3rd power, remember it's to the x power, times 4/5 to the n minus x power, so 10 minus 3 power. So basically 3 successes or 7 failures. These exponents always had to add up to the total number of trials. So this is going to be a 7, right? And then 7 and 3 make 10. All right, so I'm going to go ahead and rewrite that though, just so it looks better. So we have 10 choose 3, 1/5 to the 3rd, and then 4/5 to the 7th. And then we will calculate that probability. So that probability is going to be 0.201. Again, you can use this, calculate the 10 choose 3 on the calculator. You could do this on the calculator. Most scientific calculators have that function. All right. So let's look at another example. So a survey from Teenage Research Unlimited, Northbrook, Illinois, found that 30% of teenage consumers receive their spending money from part-time jobs. If 5 teenagers are selected at random, find the probability that at least 3 of them will have part-time jobs. So it says that 30%, so they're saying that at least 3 have part-time jobs. So part-time jobs is considered success, which means that the number of successes here, it says at least 3. So if it's saying at least 3, this means that the number of successes x has to be 3 or greater. At least means 3 or greater. So it has to be greater than or equal to 3. So you have to be able to interpret that statement there. So we have multiple values here. We could do 3 or 4 or 5. So we could do x is equal to 3 or 4 or 5. Why do we stop at 5? Well, because we only got 5 teenagers that we can do it for, right? So we have to stop at 5 because we only got 5. So 5 teenagers, that's my number of trials. So n is equal to 5 here. So basically we want the probability that x is greater than or equal to 3, which means that we need to do the probability x is equal to 3 or the probability that x is equal to 4 or the probability that x is equal to 5. So remember, or means that you add the probabilities together. That's the addition rule for probabilities, the general addition rule. So now we add those probabilities. So we're basically using the binomial formula 3 times essentially. So we have here, we're going to apply the formula here. We have 5, choose 3. Now the probability of success is 30%. Right here it says there's 30%. So that's going to be P is 0.3, which means that Q is 0.7. Remember, they have to add up to 1. So we have 0.3 raised to the, how many successes do we have? We have 3 successes times 0.7 raised to the, how many failures? Well, 5 minus 3. Plus, and then repeat that for x equals 4. So 5 choose 4, 0.3 to the 4th, 0.7 to the 5 minus 4th power. Do that for the last one. 5 choose 5, 0.3 to the 5th, 0.7 to the 5 minus 5. And then we're going to go ahead and plug those in, of course, and then get a probability. So the probability is going to add up to 0.162. Alright, so calculating those 3 probabilities from the last problem, you can kind of tell that it's kind of tedious because the fact that we had to calculate 3 probabilities. So what if that turned into 4 or 5 or 6 probabilities or more? Well, in that case, instead of actually doing the calculations individually and then combining them, we can actually combine them. We can actually find them using the binomial distribution table. There's actually a table that you can use to find the probabilities right away because they've already been calculated for you. And then you could just add those 3 values together or whatever values you have. So for instance, if we had, for example, in the example that we had earlier, we had 5 teenagers, right? So n is equal to 5, and the probability of success in this case was 0.3. So we're going to go ahead and find the intersection of those. Now, if you want, for example, and we wanted in this example 3, 4, or 5, right? So we're looking at 3, 4, or 5, which means that we're going to be adding these probabilities together. This is the probability. This is P of 3, and this is P of x equals 4, and then this is P of x equals 5 in our example earlier. And notice that if we add those together, we're going to get the answer that we got earlier, which is the 0.162. So if you add that up, you should get the answer that we got earlier. So that's how you go about using the binomial distribution table, which simplifies things immensely. So let's look at an example where we use the table. Public opinion reported that 5% of Americans are afraid of being alone in a house at night. If a random sample of 20 Americans is selected, find the probabilities, the following probabilities by using the binomial table. There are exactly 5 people in the sample who are afraid of being alone at night. So if we wanted the probability of 5 people afraid of being alone, well, we have the probability of success is 0.05, so that's P is 0.05. We have a total sample of 20 Americans, so N equals 20, and then we have exactly 5 people, so X equals 5. So we can use those values. So for part A, we're looking for P of X equals 5. In that case, or X equals 5, so we got a probability of 0.05. We got 20 people in this table, and then we're looking for X equals 5, which means that this is the probability. And it's as simple as that. So now part B, instead of actually calculating and using the formula, you can use a table. Now for part B, there are at most 3 people who are afraid of being alone. At most means that you have the most that you can have is 3. So that means you can have 0 or 1 or 2 or 3 people. So this means that X is equal to, you could do P of X equals 0 plus P of X equals 1 plus P of X equals 2 all the way up to 3. So at most means that X is less than or equal to 3. That's what at most means, okay? So then we're going to be adding those 4 particular values for this problem. So we're looking at, if we go back to the chart, now we're looking at X equals 0, 1, 2, and 3. So we're adding up these 4 probabilities. So it turns out if you add those 4 probabilities, you're going to get 0.984. All right, so let's look at part C. There are at least 3 people in the sample who are afraid of being alone at night. So this says at least 3 people. So that means you're looking at the probability of greater than or equal to 3. So that's P of 3 plus P of 4 plus P of, and then how many people do we have? Oh, that's a lot of Americans, right? So at least 3 means that you're going to be doing all the way to 20. All the way to 20. However, are we really going to do all the way to 20? No, we're not going to do all the way to 20. What we're going to do is we're going to go from 0 to 2. We're going to do 0, 1, and 2. And then we're going to get those probabilities and then take that away from 100%. And that will give us the rest of it. Okay, so what we're going to do is we're going to do the opposite of greater than or equal to 3. The opposite of that is less than 3. So we're going to do 1 minus the opposite. So if we get the opposite of that, subtract from 1, we get the rest. So we're going to be doing 1 minus P of 0, P of 1, and P of 2. And that will save us a whole bunch of time because now we only have to add up those 3 probabilities. So we're going to be adding up these 3 probabilities and then subtracting it from 1. So if we do that, if we add those up, you get 0.924. 1 minus that is 0.076. So a little trick to save some time there. You could of course add up those 17 numbers, but that would be a pain. And so we did a shortcut using, this is called the complement rule that we used here, the complement rule. All right, so the next thing is we're going to actually calculate the mean, variance, and standard deviation for the binomial experiment. So just like with other variables, we can find the mean, variance, and standard deviation for random variables, just like we did with the variables in the beginning of the year when we talked about more like in chapter 2 when we were doing, mean, standard deviation for those variables. So we're going to be doing it for the binomial distribution. Remember, just to kind of refresh your memory, the mean represents the average or expected outcome and is also known as the expected value. So the mean is a typical value to be expected. The variance and standard deviation represent how spread out the outcomes are from the typical or expected value. So if you want to calculate these 3 quantities, you're going to be using these 3 formulas below. So the mean formula is actually very simple. You take the number of trials and you times it by the probability of success. Variance and standard deviation are actually quite simple as well. You're basically going to calculate the mean, from here, and then you're going to multiply it by Q. And that's how you get the variance. Now, if you want the standard deviation, you just take the square root of the variance to get that. So to find this, you just take the square root of the variance here, and that will give you the standard deviation. So these three quantities are actually pretty simple to find. So let's do an example of that. An 8-sided die is rolled 560 times. Find the mean, variance, and standard deviation of the number of 7s that will be rolled. So if we want the mean, remember the symbol for the mean is mu in this case. We're looking at population mean. The symbol for variance is sigma squared in this case, and then standard deviation is sigma, just sigma, lowercase sigma. So if we want to find the mean, well, the number of trials is 560. And the probability of success here for the number of 7s is 1 out of 8, because there's only 1 7 out of 8 numbers on the 8-sided die. So we have here 560 times 1 out of 8. Remember that the formula was n times p. I'll go ahead and write it out here. So basically, you're just going to multiply, this is over 1, multiply numerator to numerator, denominator to denominator. And you're going to go ahead and divide those, and you get 70. So the average is 70 for the number of 7s that will be rolled. Now, if you look at the variance, that's just going to be whatever we got for the mean, because this part right here is the mean, right, mu, and then multiply that by q. So we got 70, so we're going to plug that in there, save some time. So we got 70 times q. How do we find q again? Well, we know that p is 1/8, so q has to be 7/8. So 1 minus that. So we're going to do 7/8. And then we got 70 times 7 is 490. And then 1 times 8 is 8. And then we're going to go ahead and divide those numbers. So if you divide those numbers, you're going to get 61.25. So now we're going to do the standard deviation, which is the square root of NPQ, or the square root of whatever we just calculated. We get about 12.522. So those are my quantities here. So again, to interpret this means 70 is the average number of times that you're going to get the number of 7 if you roll an 8-sided die that many times, 560 times. So if you roll it 560 times, you can expect on average 70 7s. And this is, of course, if you repeat this experiment multiple times, on average you get that many 7s. Now for the sigma squared, in the sigma, let's look at the sigma. The sigma is the easiest one, is pretty simple to interpret as well. The 12.5 is saying that 12.5 is the typical distance from the average of 70 for each outcome. So for example, some outcomes can have 70 minus 12.5 7s, for example, on average. So some outcomes can have, what is 70 minus 12.5? 70 minus 12.5 is about 57.5. So on average, you can have about 57.5 7s when you roll, or you can have 70 plus 12.5, or 82.5. So these are just averages, of course. So on average, you're expected. You can have you can have 57 7s, or 58 7s, or 82 7s, and then they basically average out to about 12.5 when you're looking at the different amount of 7s when you do this trial multiple times. So the higher this number, the higher the spread, right? So, and we don't want that number to be too spread out. I mean, because if it's too spread out, that means that it's kind of hard to stay on target, because it varies so much, right? So just kind of thinking about how the graph looks like in this case. So if you had the average to be about 70, Well, if this number is high, well then this graph is going to be pretty spread out. So it's going to be actually going to be more like this. It's going to be flatter. So if this is like y normally, then it's going to go flatter if it's more spread out. Just to give you an idea of the, the picture of the graph. All right, guys, that's it for the lesson. That's how you calculate mean, standard deviation, and variance, as well as calculate the binomial probability using the table and the formula. Hope you guys learned something from this video, and I will see you in the next one.